we have one sample t confidence interval. Okay, here we are talking about one sample t test. We have two sample t test as well. Okay, but right now just focus on uh, t confidence interval just for one sample. Okay, why we are using t distribution? Because we have a small sample less than 40. Okay, so it is very similar to Z intervals. Only difference is here you have T instead Z. Okay. So this piece, sorry, T alpha over 2 n minus 1, we call critical value for T n minus 1. Okay. So this n minus 1 mean degree of freedom. Okay. Alpha over 2 is the uh, probability value. Okay. So once we check an example, you can see here in this example we have 10 soda cans, which means n equals 10. They have given S and okay. Sorry, this question this should no, this should not be there, right? Just talking about this one. Okay, if it is normal distributed, then we can assume that our sample is normal distributed. Okay, but actually in this question I think it is there because sometimes although our population is normal distributed, but sample size is very small, not very small, it's small. For an example, less than 30, something like that. We do not consider our sample is normal distributed because it is not enough to consider like that. Okay, so at that time again we use T distribution. Okay, it doesn't matter or whether this is normal distributed or not. If you have very small sample, then you have to use the T distribution. So degree of freedom, you have 10, so degree of freedom n minus 1, it is 9. Alpha over 2, since we are dealing with confidence interval, you have to take alpha over 2. What is alpha? Alpha is 0.05, right? Because it is 5%. So alpha over 2 is 0.025. Okay, alpha over 2. So go to the table and find this value. Okay, I think last time I showed you, right, how to get the value. Okay, so that value is 12.09. So this is a T value, like C value, it is a T value. That values can be larger than C values. Okay, so again you have your interval. Okay, this is, yes, T interval. So this is the confidence T confidence interval. Normally we call this T confidence interval. Okay, once you check the same example with the C confidence interval, I think if you remember, those are the values for C confidence interval. Okay, we did this in the class. Uh, if we assume that it is normal distributed and we consider our sample is also normal distributed, then we get the C confidence interval for the same example. So you can check these values for T confidence interval value and C confidence interval values. So you can see, I think they have shown this, yeah, in the correct scale. T confidence intervals in general, T confidence intervals are much wider than Z confidence intervals. Okay, for the same under the same scenario. Clear? Okay. Increase the n. That's the best. I mean, the best choice is to consider C, because you can see here, if you get C score, it is much more smaller than the T confidence interval. So if you remember, I told you we try to keep our interval smaller. I mean, try to keep our interval as much as we can smaller than the other intervals, right? So we try to keep it like minimum width. If we can keep it minimum width, that's the best choice. Okay, but the problem is this. If we go if we go for small samples, that sample does not follow the normal distributed normal distribution, or we call it it doesn't follow uh, normality assumptions. Okay, so in that case, if we use C intervals, sometime it gives most of the time, not the sometime, most of the time it gives us wrong answers. I mean, our actual mu not inside this interval. It's going to be like outside the interval, something like that. So to avoid those kind of problems, we use T instead of Z for small samples. Okay, that's the idea you can get here. Clear? Here we have considered this C because of this, because they have mentioned here, see, population is normally distributed. You know, when population is normally distributed, without any problem, we can consider our sample is normally distributed, and we can deal with normal distribution case. Okay, so only thing is why I have mentioned Z, because of this. Clear? If you don't have this, then there is no C intervals. Clear? So talk about this one. Our T interval is like this. Okay. Okay. So what is why this is? Okay. Where did that guy come from? 2.262. It came from this value from the T table. This is the X bar. See, they have given this value from the T. Do I need to show you? Okay, T alpha over 2. Okay, I'll show you this one. T alpha over 2 means 0.025, right? Degree of freedom is 9. So I need to find T 0.025 and degree of freedom 9. Okay, go back to this table. So what is the alpha? This one. Is that correct? So what is the I mean, not alpha, sorry, alpha over 2, right? So alpha over 2 is 0.025. What is the degree of freedom? 9. So 9 is there. So once you come back, once you go along this horizontal axis and come down along this vertical axis, you can pick this value, right? So this is the value which belongs to T alpha over 2, comma, our degree of freedom. Our degree of freedom is 9. Okay, 2.262. So I think that's the value here. See? Okay. Okay. Let me go. Okay. Same as the confidence bound, we have T confidence bounds. Since we are dealing with one sample, we call it one sample T confidence bound. Again, confidence bound mean it is either upper bound or lower bound. Okay, just one. Upper bound or lower bound. We call upper confidence bound for upper bound, lower confidence bound for lower bound. Okay, still we are dealing with mu. Okay, so at that time we don't have alpha over 2 because we are just considering alpha, this piece. If it is upper bound, we are considering this, so it is just alpha, no alpha over 2, because there is no confidence interval. We have only confidence bound, either upper bound or lower bound. For this case, it's going to be like this, alpha. Okay, that's why we have alpha. Degree, this is the degree of freedom. if you remember, we assume that we don't know population standard deviation. Okay, that's why we have S instead sigma. Okay. Okay. This is the last part of this section. Prediction intervals. Sometimes we need to predict something. Predict what will happen for our next. If we add another observation, if we add the next observation, what will happen? If we have 100 observations, okay, then we find our intervals and do whatever. Okay, but what happen if we have another observation, or we believe that we have another observation, which means 101. Okay, 101th observation. What will happen if we add the 101th observation into our data set? So at that time, we can predict the interval. Okay, we can predict our interval without doing all the stuff what we have done. Okay, so these are samples, or we can consider just population, different samples from the population. So population mean population variance equals sample variance. Okay, because we consider they are independent. Do you remember those assumptions we made? They are SRS, simple random sample, normal distributed. See, they have mentioned normal distribution. They are normal distributed. So just consider point predictor. This is just a point predictor. Okay, for this one, point predictor for xn plus 1, which means next next observation, xn plus 1 equals xn plus 1. Okay, xn plus mean next one, next observation. Okay, is x bar. Point predictor is x bar, which means we assume that point predictor, we assume that it is x bar for the next observation. So with prediction error, there may be a prediction error. Okay, so prediction error we can find using those using the difference between predictor and the actual value, right? So this is the predictor, this is the actual value. So this difference gives us the prediction error. Okay, what happens if I need to find the expected value of this? If I need to find, why do I need to find the expected value? Do you remember in the section in the chapter 6 we deal with point estimators, right? If that particular point estimator is unbiased, right, how did we find it? Using by taking expected value, right? So something very similar here. We just need to find the expected value. So we take simply expected value of what? This prediction error. This is the prediction error. Okay, this is the prediction error. Since they are simple random sample, okay, so one observation doesn't has nothing to do with the other one. Okay, so they are like independent, so we can get expected value like this. Okay, we can give expected value for both of them separately. This one, expected value of x bar. Do you remember expected value of x bar? Expected value of sample mean. It is same as the population mean. Okay, it is same as the population mean. Once we get the sample mean, we call it x bar, right? Once we get the samples mean, okay, there are few samples, sample 1, sample 2, sample 3, like that. So each of them, they have x bar, their sample mean is x bar. But what happened, the mean of all of them, when we collect all these samples together and calculate the mean, that mean equals to the population mean. Okay, that mean equals to the population mean. So that's why this becomes mu, population mean. Again, this one, next observation, it is again another sample. Okay, next observation, it's another sample, right? It doesn't matter, it's just one observation. We can consider it as a separate sample. Okay, same here, its mean equals to mu. Okay, population mean. So this difference 0. Okay, which means not this difference. Expected value of prediction error is 0. Okay. Okay. I told you these two guys, x n plus 1 and x bar. I mean these two, they are independent, right? Why they are independent? Because we are considering simple random samples. So one sample has nothing to do with the other one. Okay, so they are independent. Since they are independent, once we calculate the variance, okay, let's check this one, x bar. Since if we calculate the variance of prediction error, okay, n plus 1, this one, this equals to, okay, variance of x bar plus variance of x n plus 1 minus 2 times covariance x bar comma xn plus 1. I mean covariance between those two values or two variables. Okay, in this case they are independent. Since they are independent, covariance is 0. Okay, there is no covariance if they are independent. So this piece here goes to 0. That's why we have this. Okay, because they are independent. So we have variance of x bar plus, see this one, variance of the other one, xn plus 1. What is the variance of this one? It's one sample, right? So variance same as the population variance. So it is sigma squared. Okay, what happened this guy? Variance of x bar. Variance of x bar mean variance of summation xi. What is this x bar? X bar mean xi over n, right? Right. So once you calculate this, I think if you remember that, right? It is sigma squared over n, because this n comes out like 1 over n squared. So you have variance of summation xi. So inside this, it gives sigma squared, or sorry, n times sigma squared. So you will get sigma squared over n, sigma squared over, yeah, n. Okay. So we can simplify it a little bit. I mean, take out the sigma and you will get this. X bar is, okay, let me write it again, xi minus, sorry, xi over n, right? X bar mean this part, this one, sigma
Yes.
xi over n. Once you simplify this, you will get 1 over n squared variance of sigma xi, which means for this case, I think you need to expand this. Okay, I think this was in your chapter. I don't remember the chapter, but it should be there. So you can give variance of each xi, x1 here, plus variance of x2, plus up to variance of xn, because they are independent. So here it is sigma squared, here sigma squared. So you have 1 over n squared times n times sigma squared, right? So this n cancel with this, so you can get this. Okay, so how we derive or how we define this prediction interval? If we have, okay, in this case, for a moment we can consider we have C intervals as well as T intervals. Okay, it doesn't matter. Same way, although I mean, if we have C intervals, which mean we have normal distribution, then the prediction interval looks like this. Okay, what is this? This is prediction error. Okay, prediction error. Minus 0. Minus 0. Why minus 0? Because do you remember expected value of this piece? Expected value of prediction error is what? 0, right? Mu minus mu, it is 0. Here, normally we consider expected value of prediction error, x bar minus x n plus 1. In our case, it is 0. Clear? Sometimes, I mean, I don't think in your case, but sometimes in general, we will be having a value for expected value of this prediction error. Okay, which means there is a prediction error as well. Okay, that's why they have mentioned this 0 here. Otherwise, it is useless to mention 0 here. Okay, so sometimes we will be having a value for this. Okay, okay, over sigma squared 1 plus what is this? This piece variance of x bar minus xn plus 1, right? From the last slide, square root of that. Okay, what happened if we have a t distribution? So this is not c anymore, this is going to be t, capital T, equals same here, but do you remember if we go to the t table, t distribution, we don't have sigma, right? We don't have population standard deviation. It is unknown, so that's why s came to play here. Okay, you can take it, you can keep it inside the square root or take it out there. Okay, so you have t distribution, t at minus 1 mean t and this degree of freedom. Okay, this is the degree of freedom. Clear? So although you have although you have C, you have to use the same prediction interval, same as T, with small difference. With the small changes. Okay, clear? Let's check this one. Okay, prediction interval. This is we call prediction interval. Okay, see, once you so prediction interval for what? Do you remember prediction interval for mu, right? So prediction interval for mu, if you need to find the prediction interval for mu, you have to what? Isolate prediction interval for what? Prediction interval for, let me go back and show you prediction interval for so it's not there. Prediction interval for what? For this one, because now we are dealing with prediction interval for our new observation. Okay, so that's why I just want to mention here, since we need a prediction interval for this guy, let me erase these things. Okay, prediction interval for this guy right here, what you have to do? You have to do the cross multiplication and isolate that guy. Okay, something like that. So if you do that, you can get something like this. So your capital T, it becomes like this one. Since it's an interval alpha over 2. Okay, it is just cross multiplication. Cross multiply whatever you have here, isolate xn plus 1. So you can get the prediction interval pi for xn plus 1 using this. Clear? Prediction interval for this one, 100 1 minus alpha %. Okay, so confidence level, it is 100 1 minus alpha %. Any percentage, 95 90 99 whatever. Okay, so same as upper confidence bound and lower confidence bound, same thing here. For the upper confidence bound, it is x bar plus t alpha n minus 1 s 1 plus 1 over square root of n. Okay, so you know how to deal with that. Upper confidence and lower confidence just for negative value. Okay, similar as what we have mentioned in the 3-4 slides back. Okay, clear? Just check this example. Here you have 8 observations. Okay, 8 observations. They have mentioned here. According to that 8 observations, you have its mean, sample mean, and sample standard deviation. So what happened if you need to get the prediction interval for 9th random selected participant? 9th observation. Okay, 9 is not there. There is only 8. So what you need to do? Just plug the value for what you have taken here. Okay. So T alpha is it is 95%. So alpha is 0.05. Alpha over 2 is 0.025. Degree of freedom n minus 1, it is 8. Okay, so once you go to the table and you can find 0.258. Okay, that value is this one. X bar is 98. See, they have given it, and yeah, they have given it. Okay, so simplify it. Okay, remember this one. It is n. Okay, please do not include the new observation. Okay, it is just what we have already. Okay, so this is the prediction interval for I mean 95% prediction interval for x plus 1. Ninth observation. Okay, ninth observation. Okay, any questions? Let's this is the last section in chapter 7. Confidence still we were talking about like confidence interval for mu, CI4 mu, or last slide you saw for xn plus 1, a new observation. Okay, new observation. What happened? Confidence interval for variance, same as the standard deviation, doesn't matter. Okay, what happened? We consider confidence interval for variance. Let's check that. If we consider variance, confidence interval for variance, it's gonna be like different. It's like a different story. Okay. Usually, yes, this is usually less interest. Okay, we don't do this, but I would say sometimes yes, you need to know how to deal with variance as well. Okay, so this is what they have mentioned. No need to worry about that. Okay, distribution of S squared. So last time I told you, okay, not last time. Check this one. What is S squared? If you remember, I from 1 to n, xi minus x bar squared over n minus 1, right? This is S squared. Clear? Here, they have just what? Cross multiply by n minus 1 and divide both sides by sigma square. That's how we have how they have taken this equation here. Okay, from here to here, you know how to get this one. Clear? Cross multiply by n minus 1, both sides divide by sigma square. Okay. Okay. Why we get this? You will see a few seconds later. Okay. I told you in chapter 6, once we consider the point estimators, S squared is not a point estimator of sigma squared, right? It is a biased estimator, right? But still we use that, right? Okay, let me erase this one. Oh, no. This piece right here, left hand side, it has a distribution. Okay, it has a perfect distribution. We call it chi-square. Chi we denote like this, or you can denote it like this, whatever. It's not X, it is not capital X, it is something like curly X, something like this. Okay, see, not just chi, we call it chi-squared. Chi-squared because of this squared here, right here, because of that. There is no table like chi table. Okay, the table is chi-square table or chi-square distribution. Okay, with this guy, degree of freedom, same as the T, degree of freedom is n minus 1. Okay, so this piece right here, it has a chi-square distribution. Since this left hand and right hand side are equal, then this guy also has what? N minus 1 S squared over sigma squared. This guy has, okay, this guy has chi-square distribution with degree of freedom, okay, with degree of freedom n minus 1. Okay. This is the notation for that. Last time I didn't mention alpha here. You can mention alpha as well. Okay. So we call chi-square critical values. This is what we call chi-square critical value because of this alpha. Okay. Chi-square critical value. You can find these values. There is a table in the appendix called chi-square table. Okay. Chi-square is not a symmetric distribution. Okay. Chi-square is some kind of skewed distribution, positive skewed, or we call right tail skewed. I mean right skewed, something like this. So last, standard normal distribution or T distribution, not T, standard normal distribution, we use the property of symmetry, property of symmetricity to get the values. For an example, alpha over 2 probability for the alpha over 2 is C alpha over 2 equals C negative alpha over 2, right? They have same value, but here it's different. Okay, don't think like that, it's different. Okay, check this one. This colored area is alpha. Okay, whatever here is what? 1 minus alpha. Okay, so same here. If you have this piece like alpha over 2, and again, yes, this piece alpha over 2. So what is inside? 1 minus alpha, right? If we need to find the probability between these two, alpha over 2 pieces, then we have to find 1, that is equals to 1 minus alpha. Okay, clear? Okay, next slide I'll show how we deal with that. This is the chi-square table. See, they have mentioned this is the chi-square value, that corresponding value. If this area is alpha, is the value. So you need here this side, they have mentioned alpha values. Check this one. First value start from 0.995 alpha value. Okay, which means alpha values are decreasing from left to right. Okay, so doesn't matter. First row, first column, it is degree of freedom. Okay, you have, I think, up to 40. You cannot see it, up to 40. Yeah, 40 values. Okay. Okay. How we consider this confidence interval? 100 1 minus alpha % confidence interval for sigma squared. Okay, so critical value is 1 minus alpha. So I told you, if we need to get the, this is alpha over 2, this is alpha over 2. So actually we need whatever inside here, right? We need that probability, right? If my variance is bounded, so we need whatever this one. I cannot show it, color it. Okay, I color it like this. We need this. What is this? 1 minus alpha. So the probability of what we need is equals to 1 minus alpha. So what we need sigma squared, but we don't have sigma squared. We have this guy bounded from here and from here. These two pieces, they are chi-squared. This one left hand side on 1 minus alpha over 2 comma n minus 1, and this one chi-squared alpha over 2 n minus 1. That's why these two like this. So we need the probability between those two. That equals to 1 minus alpha. Clear? So what you need? This guy, variance. So if you need variance, sigma squared, you have to what? Isolate this one. Isolate sigma squared, right? So you can flip this inequality or deal whatever you won't anyhow get this one. Okay, easiest way is what? Uh, I mean, flip this one, this equation, like 1 over this first one. So at that time, if you flip a fraction, what will happen? This inequality, it changed, right? It flipped the other side. So this is going to be sigma squared n minus 1 s squared, this side 1 over whatever you have here, this one. Okay, so now you can do the cross multiplication and get this one, not whatever, this one. Okay, so I forgot to show you. Okay, for an example, let's say you need to find chi-square. I'll show you one value like 0.1. Okay, degree of freedom is 5. So degree of freedom is 5, which means here this guy. Alpha value is 0.1, this one. So corresponding value is this. Okay, value is 9.236. Clear? Same as how we deal with the other tables. We have to get the value. Okay, now let me erase this, and this is what you need. From this, sorry, you can get, okay, 100%, sorry, 101 minus alpha percent Ci for sigma squared is, simply you can write using brackets. Okay, so n minus 1 s squared over chi square alpha over 2 degree of freedom n minus 1 comma upper bound is again n minus 1 s squared chi square 1 minus alpha over 2 n minus 1. Okay, alpha given like okay, confidence interval for 95%. Okay, then what is alpha? Alpha is 0.05. So again alpha over 2 is 0.025. So you have to deal with 0.025. So at that time your alpha is alpha over 2. Or in this case your alpha is, I mean, simply 1 minus alpha over 2. Here 1 minus, okay, here 1 minus.
Okay, okay. Thank you, sir.
Here 1 minus, okay. 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 So confidence interval for sigma squared is this. You know what is the relationship between sigma square variance and standard deviation. So for the standard deviation, confidence interval is this. Just take the square root. That's it. Okay. Clear? So 1 minus alpha percent confidence interval for population variance is this. Either this one, no, previous one, doesn't matter. Okay. I think I can do this example. I have enough time. Yes, I can do this example. Expansion, my sample is 9. Pass power gas ship container. Standard deviation. Sample standard deviation was this much, 2.81. Assuming normality, okay, assuming normality, derive 95% confidence interval for this guy. So you can take, automatically you can take this guy as well. So how do you get that? What is the equation for n minus 1 s squared, right? N minus 1 s squared chi squared alpha over 2 n minus 1, right? This guy n minus 1 s squared chi square chi square 1 minus alpha over 2 comma n minus 1. So alpha over 2 greater than, I mean not greater than, sorry, chi square alpha over 2 degree of freedom n minus 1 is, that value is greater than chi square alpha over 2 sorry 1 minus alpha over 2 degree of freedom n minus 1. Okay, this left hand side value greater than the right hand side value, so that's why this piece the left hand side piece become smaller than this piece. Okay, you can see otherwise numerator is same, but denominator is different because the right hand side guy, this guy, denominator is greater than, sorry, is smaller than a left hand side guy. Okay, so once you check the chi-square value, you will see that. Okay, so simply let me erase this. Simply plug the values. So S, you know, they have given n given alpha is 0.05, so alpha over 2 is 0.025. 1 minus alpha, you can take like this. Okay, so chi-square alpha over 2 is this much, and chi-square 1 minus alpha over 2 is this. Okay, okay, I can show you just one. Let me check this one. Okay, alpha chi-square 1 minus alpha 2 will mean 975. 975 n minus 1 is 8. Okay, so I need to find 0.975. Chi-square 0.9.5 n minus 1 is 8. So I need to find this. Okay, so let's go to the table. 9758. So where is 975? Here. See, and 8, right? So I think this is the value, 2.180, right? So that's how we find the values. There is a small, I mean, it's not hard to see. Once you go from left to right, you can see values are increasing. Okay, so that's why I told you large chi-square alpha values are smaller than the other values. Okay, it depends on how we select that, how we pick the alpha. Okay, so plug the values, then you can get this. So this is the 95% CI for sigma square, and you can get the standard deviation. I mean 95% confidence interval for standard deviation by taking square root. Okay, to get the square root, you know, you cannot simply find the square root, just use your calculators and get the value. Okay, in general, try if in your questions, if they haven't mentioned how many decimals you need to keep, try to keep at least, I mean, don't go more than 4, just try to keep 4 decimal places. Okay, that's the best way, that's a good practice. Okay, try to keep it at least 4 decimal places unless they have mentioned. Okay, okay, so that's the end of this chapter.